All right, gearing up for that 2026 physics exam, let's talk about moving charges and magnetism. You know it's a beast, especially when it comes to the derivations. So this isn't just going to be a simple review. Think of this as your strategic playbook for mastering the derivations that are going to score you the most marks. Let's get right into it.
So, here's the big question, right? The one everyone has? With so many formulas to learn, where do you even start? Where should you focus your energy? Most people just guess, but we're not going to do that. Nope. We're going to use data to figure out exactly which derivations are your high-value targets.
And here it is. Take a look. This table is based on recent CBSE trends, and it shows you exactly what gets tested the most. See that top one? The field of a straight wire? That shows up in half of the papers. Wow. And right behind it, you've got the Lorentz force and the force between parallel wires. See? This isn't about studying harder, it's about studying smarter, focusing on these big ones. You know, what's really cool is how these all group together. You can basically think of this entire chapter in three main clusters. First, you've got Lorentz mastery. That's the biggest chunk, about 40%. Then comes Biot-Savart and Ampere, which is all about calculating fields. And finally, devices, where you see how it all gets applied. Seriously, if you can conquer these three areas, you've pretty much conquered the whole chapter.
Okay, so let's start with the biggest piece of that pie, mastering the forces on charges. This is the absolute foundation. Everything else is built on this. And honestly, it's where most marks are either won or lost.
All right, mission number 1, the Lorentz force. This is one of the most frequently tested concepts, so listen up. This formula, well, it describes the fundamental force on any charge that's moving through a magnetic field. It's incredibly powerful, and you absolutely have to know it for the exam.
So when you're writing this out in the exam, a perfect answer always has 3 parts. First, you just state the law in its vector form. Easy. Second, you mention that you find the direction using the right-hand rule. And third, and this is important, you write out the magnitude and you make sure to include that sine theta term. It's simple, it's clean, and it's super effective.
Okay, listen up, because this is a classic trap. So many students just forget the sine theta, but it's absolutely crucial. I mean, it's the whole reason the force is 0 if the charge is moving parallel to the field. The other big mistake? Forgetting to flip the force direction for negative charges, like electrons. Don't let these simple mistakes catch you out.
And here is a little tip to really impress the examiner. After you've written down the formula, just add one short sentence. The force F is perpendicular to both the velocity v and the magnetic field B. That's it. It shows you haven't just memorized the formula, you actually get the geometry of what's happening. It's a tiny detail that signals a much deeper understanding.
Okay, next up, another really common derivation, the radius of circular motion. So when that Lorentz force acts on a particle just right, it can pull it into a perfect circle. And this formula, it tells us exactly how big that circle is going to be.
You know, this derivation is just beautifully simple. The whole key is just realizing that the magnetic force is the centripetal force. It's providing that inward pull. So you just set them equal to each other. mv squared over r equals qvb. Then you just cancel out a v, rearrange it to solve for r, and you're done. It's honestly that easy.
And here's another pro tip for you. Always start by stating the condition for circular motion. The velocity has to be perpendicular to the B field. That's what makes the angle 90 degrees, so sine theta becomes 1. When you explicitly state that and then clearly show the V canceling out, you're showing the examiner that you understand every single step of the process.
All right, so we've totally mastered how fields affect charges. Now, let's flip the script. Let's move on to our second big concept cluster. How do moving charges or currents create these magnetic fields in the first place?
And now we come to the one that, according to our data, is the most frequently tested derivation of them all, the field of a long straight wire. This is the absolute classic application of Ampere's law. It describes how that magnetic field wraps in circles around a wire, getting weaker as you move away. You have to know this one inside and out.
This derivation is the perfect showcase for the power of symmetry in physics. You start with Ampere's law. Then, by choosing a clever path, a circular Amperian loop, you make the problem easy. Because the B field is constant along that path, that tricky integral just simplifies to B times the circumference, 2 pi r. You set that equal to mu0 I, solve for B, and boom, you have your answer.
Okay, let's talk about a really common point of confusion, the solenoid versus the toroid. Their formulas look kind of similar, right? B equals mu0 Ni for the solenoid, and B equals mu0 Ni over 2 pi r for the toroid.
Mixing these up is an easy way to lose marks, so you've got to know the difference cold.
So let's just break it down side by side. For a solenoid, the field inside is pretty much uniform. It's the same everywhere. But for a toroid, you can see from the R in the formula that the field actually depends on how far you are from the center. The one thing they have in common? For an ideal version of both, the magnetic field outside is practically zero. It's all neatly contained inside.
All right, now let's see how all this theory gets put to work. It's time for our final cluster, devices. This is where we see these principles become actual technology, like in electric motors and other cool gadgets.
Okay, next up is the principle that literally makes electric motors turn, the torque on a current loop. This formula explains that twisting force a coil feels when it's in a magnetic field. It's the absolute heart of devices like the moving coil galvanometer.
Now, the most elegant way to handle this derivation is to first introduce the idea of the magnetic moment, which we call mu. It's just a way of packaging up the properties of the loop, N times I times A. Once you have that, the torque is simply the cross product of that magnetic moment and the B field. When you expand that out for the magnitude, you get the full formula, NIAB sine theta.
And here's how you can connect this to the bigger picture to really show you know your stuff. In a moving coil galvanometer, they use a special radial magnetic field. And the whole point of that is to make sure the angle theta is always 90 degrees. Why? Because that maximizes the torque for any given current, and that's what makes the device so incredibly sensitive. Mentioning that connection shows you're thinking way beyond just the formula.
Okay, we have covered all the core derivations. So now, let's pull it all together into the ultimate exam checklist. This is what you need to review for your final prep, the critical do's and don'ts for exam day. First up, the traps you need to avoid. We already talked about forgetting sin theta and reversing the right-hand rule for electrons. Don't do it. For parallel wires, just remember this. Same direction attracts, opposite repels. And of course, always use consistent SI units, and make sure you choose the right Amperian loop to match the symmetry of the problem. Avoiding these will save you so many easy marks. And now for the moves that will secure you those top marks. 1. Always state the law you're using by name, according to Ampere's law. 2. Define your variables, especially things like N equals N over L for a solenoid. 3. Mention the key conditions, like V being perpendicular to B. 4. Connect the force per unit length formula back to the official definition of the ampere. And 5. Label your diagrams clearly, every single vector. These are the details that scream perfect answer.
So there you have it. We've basically broken the code for this part of the exam. But let's end on a bigger thought. From the Lorentz force that curves cosmic rays flying through space, to Ampere's law that governs the fields inside every single motor and generator, these equations are literally describing an invisible world of forces that is all around us, right now. So the question is, which of these ideas most changes how you see that world? Give it some thought, and good luck with your preparation.